Most people in the bolting industry have a misconception of yield as far as studs are concerned. What we've normally seen in the field is, well, if the bolt's broken, we put it into yield. That's not actually true. On the screen, you'll see we have a stress versus strain curve. And as we put bolt load on, you'll see the stress go up. Now, the strain curve, the bolt will come back within 0.2% of its original shape. That's actually the definition of yield. Therefore, if you take the bolt past yield, you'll see deformation in the bolt, which actually means it won't recover to 0.2% of its original shape. Therefore, you've stretched the bolt past its yield point, but it hasn't broken yet. This means it doesn't hold the amount of load that we think it's going to hold. And then if you keep torquing it past, then you're going to have the stud fail. Here's a video of what happens in real life when you stretch a bolt too much.
1/8" bolt we're inserting into a Skidmore bolt load indicating unit. We're going to put it on here and we're going to demonstrate what over-yielding a stud looks like. I put it on, you'll see we're going to raise up bolt load, and this is going to continue to turn up as I tighten the bolt, and pretty soon I'll keep tightening the bolt, but I won't be getting any more bolt load. That will be an indication that the bolt has been over-yielded. So I'm turning, still going up. No longer moving up, I'm still turning. It's actually coming down a little bit on the bolt load. So this bolt has been over yielded. So we'll take the bolt loose. Bolt has been over yielded, and yet you can see no difference with your eye. And this nut will run freely up and down this stud. You cannot tell if a bolt has been yielded simply by looking at it. Thank you.
Galling is a form of wear caused by adhesion between sliding surfaces. When a material galls, some of it is pulled with the contacting surface, especially if there's large amounts of force compressing on the surfaces together. So that compression force is grinding metal on metal to stretch metal. So what we see is a macroscopic transfer of material between metallic surfaces. During transverse motion or sliding, galling occurs frequently whenever two metal surfaces are in contact, sliding against each other, especially when you don't put enough lubricant on there. On the screen, you'll see 3 different ways galling occurs. Galling is one of the most frustrating things we run into in the field, especially as assemblers. The true definition of galling comes from ASTM G40, and it says, galling is a form of surface damage arising between sliding solids, distinguished by microscopic, usually localized, roughening and creation of protrusions, i.e. lumps, above the original surface. So what does that mean to the assembler? Well, we're grinding steel on steel to stretch steel. That's what we're doing when we use torque. So if we want to get rid of galling, one of the best ways is to properly lubricate, which we will go over here in the upcoming slides. The other part of getting rid of galling is also looking at what type of lubricant you are using. That's why you've seen an increase of molybdenum disulfide lubricants or moly lubricants in the industry. We found that nickel lubricants actually cause galling because when you put heat and force on there, it generates nickel dioxide, which is a scarring agent. So most plants will be moving to molybdenum disulfide lubricant, but please use the lubricant that your plant has specified. You will see in the industry, we're getting rid of nickel lubricants and getting more towards molybdenum disulfide or moly lubricants as they create a better barrier between the two surfaces of the grinding part of the bolted flange joint. Manual torque wrenches. There are several different types of manual torque wrenches within the industry. The main one within industrial plants is a clicker type of wrench. They come with different size drives, which allows different torque values. For this demonstration, we are going to show you how to set a 250 foot-pound clicker wrench. There are potentially 2 different sets of numbers on a clicker wrench. They are Newton meters and foot-pounds. Most companies use foot-pounds as a method of achieving bolt load. In equivalent settings, foot-pounds can generate roughly 35% more torque than Newton meters. 1 foot-pound is equal to 1.36 Newton meters. Use caution and double check your intended torque setting. If you are not working in the intended setting, your bolt load will not be correct. Each assembler should check with the manufacturer on how to set their specific torque wrench. However, the most common way is to pull down on the handle and rotate the wrench. You will see the foot-pounds increase. Most wrenches have a check ball in the square drive. Match the check ball with the dimple in the socket to make sure the socket doesn't fall. It takes very little movement to achieve large bolt loads after the bolt is engaged with the flange. Therefore, using a manual torque wrench, do not keep pulling on the wrench after the wrench has clicked once. More importantly, do not double click the wrench. With each additional click of the wrench, the bolt load increases 10 to 15%. Common maintenance requirements consist of the following. When done with using the wrench, ensure that the wrench is set to its lowest setting. Note, do not exceed the lowest setting as it will damage the internals of the wrench. Calibration. Verify that the wrench has been calibrated within the time frame required by your site procedures. Torque verification periodically. It's a good practice to verify that the torque wrench can perform. Clicker wrenches are susceptible to damage if dropped or not stored properly during travel. Practices that affect final bolt load. After the flange has been assembled or pre-tightened, there are several bad practices that affect the reliability of a bolted flange joint. Improper lubrication with clicker wrenches. No lubrication. You will see that without lubricant, the bolt stress is lower than the target bolt stress of 40 KSI. This test averages at 28 KSI with a low amount of 27.3 and the high of 31. Partial lubrication. Inconsistent or partially lubricating the studs will result in unfavorable results. While the average bolt stress has increased 5.4 KSI, we still have not yet achieved our target of 40 KSI. Bolts that are not lubricated in the same fashion will have greater variation in the bolt load. Proper lubrication. Properly lubricated studs will result in a tight bolt load at our desired stress target. When lubricating, be certain that all valleys of the stud bolt threads are filled. Once the nut is hand tightened, you should see a bead of lube extruding from beneath the nut. This indicates that the lubrication has been applied to all working surfaces. Pay close attention to the bolt load. Notice how the bolt load has increased, now achieving bolt loads much closer to the target bolt load of 40 KSI. And notice how the variation of the bolt load has drastically reduced when all working surfaces are properly lubricated. Hand tightening after proper lubrication. This example has the assembler tightening a bolt with a boxed-in wrench on a 7/8 stud. Notice how the amount of load on each stud is different. We call that bolt scatter, and reliable flanges need to have a good bolt scatter in order to be reliable. Also, notice the amount of bolt stress that is present on a 7/8 stud. This is without a cheater bar attached to the wrench. If we apply the same amount of torque to a 3/4 inch bolt, we would achieve roughly 80% of the yield strength desired here. If we apply the same torque to a 5/8 inch bolt, we would achieve roughly 150% of the yield strength. Impact wrench. For this demonstration, we are going to use a battery-powered half-inch drive impact wrench to tighten a 7/8 inch bolt. This wrench puts out 780 foot-pounds of maximum torque, as per the manufacturer's literature. Also notice the amount of bolt stress that is present on a 7/8 inch stud. Our original target stress is 40% yield, but in this test, we have taken the stud to roughly twice that amount at 78.9 KSI or 80% yield. Notice that the bolt scatter is not desirable.
If we apply the same amount of torque to a 3/4 inch bolt, we would achieve roughly 135% of the yield strength. If we apply the same torque to a 5/8 inch bolt, we would achieve roughly 250% of the yield strength. Note, it is common to see 3/4 inch drive pneumatic impact wrenches in field applications, and that drive size has the capacity of almost double the amount that a 1/2 inch drive impact does. Upside down nut and damaged studs. Each nut has markings on the top side of the nut. Correct installation will show the markings facing out. If the nut has been installed incorrectly or backwards, there could be a 25% difference or more in the resulting bolt load for the same torque input. This stud has minor thread damage. While this may be difficult to see, it can greatly affect bolt load or stress values. This test shows well under specified target bolt stress.
The star pattern is the most commonly used pattern in order to torque up bolts. You're going to torque up one in every quarter. The first thing you do is tighten between 20 and 30% of your target torque on all of your bolts in the star pattern. The next thing you're going to do is tighten the bolts from 50 to 70% of your torque to all of the bolts again. The third pass is 100% of your target torque on all of your bolts. And the next passes are rotational passes or circular passes where you keep going around the flange until the nuts stop moving. Normally with spiral wound gaskets, we see that this takes about 2 circular passes. Bolting patterns we're going to look at is the modified star pattern. This pattern uses the same pattern as the legacy method or the star pattern. However, the stress levels are increased more rapidly. This allows for fewer pattern passes to be performed, which basically means less effort and less amount of bolts that you need to touch. This method has been successfully applied in limited applications across full range of gaskets and joint configurations. We see this a lot on piping and exchangers, though, in the petrochem industry. The first thing you're going to do is pass 1A. Tighten the first 4 bolts to 20 to 30% of your target torque. Pass 1B. Tighten the next 4 bolts to 50 to 70% of the target torque. Pass 1C and number 2 is tighten the rest of the bolts to 100% of your torque. You'll notice here you tighten the rest of the bolts in a star pattern until you get back to the first bolt that you touched, and then you're going to do that again and touch in the star pattern at 100%, and then you're going to start ringing the gaskets or going in circular passes. It normally takes at least 2 circular passes for spiral wound gaskets, but we say to keep torquing until the nuts stop moving.
Elastic interaction. Individual sites will require different torque settings. Check with your site supervisor to confirm the specific torque increments for your job. Begin by determining the tightening sequence and number your bolts. Then set your torque wrench to your first setting. For our demonstration, we set our torque wrench to 40 foot-pounds. Tighten the bolts in a star pattern or directly across from each other. We begin with bolt 1, then 3, then 2, then 4. Notice the difference in the bolt scatter between each of the bolts. Note that it is clearly not even. The bolt load changes slightly due to tightening. This is called elastic interaction, also known as crosstalk. Set the torque wrench to the second setting. Our setting is 80 foot-pounds. Now tighten the bolts in the same order as the first pass. Set the torque wrench to the final setting. Ours is 120 foot-pounds. Once again, tighten the bolts in a star pattern. Now, you can begin to tighten the bolts in a circular pattern with the wrench still set at the final setting. Make a second tightening pass, also in a circular pattern. As you can see, the final bolt scatter is now relatively even across all bolts.